what do you need to do? Before you talk about control, you need to talk about
orbital elements
with regards to position. Determining the position, right? First is determining the position. First, the car will figure out where it is. You understand? Similarly, before you do orientation control, the satellite has to know, it has to determine what its orientation is. Only then it can control, then it can execute a control maneuver. How do you do position determination? GPS or accelerometers. GPS, you combine GPS and accelerometers. So when you're doing the attitude determination, you need so this will include sun sensors and a magnetometer. Okay, magnetometer is, what is a magnetometer? A sensor which determines the direction of magnetic field. Okay, essentially a three-dimensional compass, three-dimensional digital compass. Okay, what is absolute? So do you understand absolute? Absolute basis. So if you're looking at, you understand attitude itself. What is, how do you determine, how do you define attitude?
the angle is made with certain
Right. So just a little bit of background on attitude. So let's say this is X, okay? And this is Y. Where is Z? It's coming, it has to come out of the, always follow the right hand rule, okay? It has to come out of the board. So this is X, this is Y, so this has to be Z. So Z is this way, okay? Now, let me do X1. Y1. Okay. So this means it's a vector, and the cap means it's a unit vector, right? Unit vector is a direction vector. Just like you have scalars are magnitudes, right? Unit vectors are direction vectors. Okay. Now let's say this is what you have done is this is how the system was initially. Okay. You've rotated it like this. You get it? About what axis have you rotated? About what axis have you rotated? Z axis. You have rotated about Z axis or Z axis. Right? Yeah. You understand why you have rotated about Z axis? See, this thing have a Z axis, this thing. If you rotate that, this is how the orientation will change. You see that? You rotate about the Z axis. Okay. By how many degrees have you rotated? Let's say theta. Correct? If this is theta, this is also theta. Now can you express, how do you express x1? What component is this?
X cos X.
X
Sin
sine theta. And this is
X cos.
X1 cos theta.
right? Look at this. What is this? What is this?
Y1 sin theta.
Y1 sin theta.
Y1 sin theta.
What is this?
Y1 sin theta. Sin theta. Sin theta.
You're sure it is y1 sine theta?
Yes, sir.
100%?
Yes, sir.
It is minus y1 sine theta. Okay. You have to understand that. Why? The x direction, the positive x direction is this, right? And the positive y direction. So these are both positive, but this is negative, and this is positive. Okay. So here we can say, hang on just a minute. So x1 is, what is the x component of this? What is the x component of this?
X1 cos theta.
x1,
Cos theta.
or I simply have to write this as, do I have to write the vector here?
Must.
Right? It is x1, or can I write this as cos theta only? Unit vector, right? So it is simply cosine theta in what direction?
X
X direction, right? Plus sine theta in, make sense? Because if I write x1, I have to write x1. What is this? 1, right? Unit vector magnitude is 1. You got it? So it simply turns out to be cosine theta in the direction of x, sine theta in the direction of y. How do I write y1? Minus
cos sin theta.
sine theta in plus cosine theta. Can I write this as well? What is the z component? Sorry. Does that make sense?
Yes, sir.
The z component, there is no z component here, right? It's only moving in the x and y plane. So the z component is 0 in both cases, right? Now what is z? Let's say there was a z1. Can I write z1 as, what is the x component of z? 0. 0 x plus 0 y plus 1 z. Okay. Now if you look at this, I can write as x1, y1, c1 equal to cosine theta sine theta 0 minus sine theta cosine theta 0 0 0 1, and this is x y. Everybody understands this? Not very difficult? Difficult? Yes? You understand, you follow this? What I did here? It is simple rotation, right? There is an orientation change. Okay. What I'm trying to get to is express the orientation of x1, y1, z1 with respect to x, y, z. Orientation, just like, do you need a reference or do you need a origin for expressing position? Yes. You express position, everything is relative, right? So you, just like that, I'm trying to express the orientation of the new orientation with respect to the original orientation. Okay, this was the original orientation, x1, y1. The new orientation is it has moved about the z-axis by an angle theta. What I did was this, the expression for this is, you resolve this into, you know the resolution into x and y component. This is the y component. This should be the x component, right? So it is, the x component is cosine theta in the x direction plus sine theta in the y direction. And there is no z component here, so it is 0. Okay. This is the relative orientation of x1, y1, c1 with respect to x, y, z. This matrix, okay, is the relative orientation of x1, y1, z1 with respect to x, y, z. So you can, and what is, about what axis was this rotated? Z axis or the z axis, right? So if you rotate it about x axis, if you rotate it about x axis, this is what you would have got. So it is 1, 0, 0, 1, 0, 0, cosine theta, sine theta, minus sine theta, cosine theta. So this changes. So if you see, this is about the third axis, right? The third row and the third column. The element in the third row and third column is 1. The remainder are 0. And then you have cosine, sine, minus sine, cosine. And similarly you have, since this is about x, you have first row, first column is 1. 0, 0. Cosine, sine, minus sine. And similarly y, you're going to get 0, 1, 0, 0, we have cosine theta minus sine theta, and this is the y. So here the negative sign moves up. Okay, that is the only change. You understand? So these are called fundamental rotations. Fundamental rotations are rotations about the fundamental axis. How many axes are there? 3 axes, right? So this fundamental rotation is about the z-axis. This fundamental rotation is about the x-axis, and this fundamental rotation is about the y-axis. Okay. Any complete rotation. Think about this. How, if you are expressing position, how do you express the position? So you have x. You'll say this is this much x, y, and z, right? So similarly, what you can do is when you do the complete orientation, you can express it as a combination of x-axis, y-axis, and z-axis. A complete rotation, and that is required. So here, this is known. Okay, this basis is known. This is something which needs to be determined. You get it? That is the reason we need this additive determination system. We need absolute sensors to determine at least 2 directions. Okay. For example, think about this. When you're in an orbit, what are the directions you can, for example, if I'm trying to, let's say you're communicating with your friend outside the class, okay, and you're telling them what is your orientation in class. How are you going to do that?
Take a reference.
Right. So think about this. If you say you're pointed, you're going to say I'm pointed to the board. Is this the only orientation?
No, sir.
I can rotate. If I say I'm pointed, if my back is pointed to the board, about this axis, I can rotate in any this thing, and that will be true. You see it? Now, if I say my back is pointing the board, my right hand is pointing to the door, it has to be this. It cannot change. I have to be in this orientation. So if I give you 2 directions, then my orientation is fixed. Okay. So in space, is there a blackboard in space? There is probably a door. No, there is no door. So what is in space?
Sun.
Sun is in space. So this could be the sun. What else? What else do we know in space?
Planets.
Huh? Planets, correct. So other planets, stars,
Other satellites.
other satellites. Magnetic field. We also know where the magnetic field is. Okay. Now, do you know where the magnetic field is? Huh? It is in the magnetic north and south. You always know where that is. Okay. So if you mount with respect to that, at this table you know where the magnetic, at this point where know where the sun is, where the magnetic field is. Now with respect to that, if I have a sensor on board my satellite and the sensor tells me where the satellite is seeing the sun and where the satellite is seeing the magnetic field, I'll know the relative orientation of the satellite. Okay, and that is the absolute orientation. You understand the absolute here, right? Now what is so for absolute orientation, absolute attitude determination, we will use sun sensors and magnetometers. You could use something like a star sensor. where you also know where these different stars are, right? So if you know two stars, 2 or 3 stars, you'll know what your orientation is. They are used, but they are on the expensive side, the star sensors or the star trackers. Okay, so we'll go with less expensive sun sensors and magnetometers. Okay. Apart from this, you'll also need incremental attitude sensors, okay, or attitude determination sensors. These are incremental attitude determination or angular rate sensors. And what that means is, let's say I tell you, first I tell you that my back is pointing to the board, my hand is pointing to the door, and then I tell you that I'm rotating about my head at 10 degrees or 1 degree per minute. After a minute, can you tell me where I'm pointed? You can do that, right? But you understand the need for this absolute? If I just tell you I'm rotating at 10 degree per minute, can you tell me where I'm pointed? And you need that initial this thing, right? The initial starting point. That initial starting point is given by these two sensors, and this will give you incremental attitude determination. How you're rotating. So at any time instance, you just integrate angular rate, and you get, what do you get if you integrate angular rate? Angle, right? So if you add that angle, you know where you're pointed at the time. Okay. And what else do you need? You actually need the GPS sensor for attitude determination. You need to know the position of the orbiting body, and at that position you can figure out what the reference attitude is first. Okay. So GPS sensor we have already mentioned that we are going to use a GPS sensor, right? We can use the same GPS sensor for attitude determination as well. Okay. So to fuse these together, we might look at an optimal estimator for fusing the absolute and incremental sensor data. Okay, so here we are looking at something like particle filter, Kalman filter, and one of you can take up one of the faculty members and a couple of students can take up this as a project where you select these sensors and get the student to work on a filter which will combine these two and get the attitude information out. Okay. Any questions until now? So this is only the attitude determination part. Okay. Now we'll talk about stabilization. What do you need for attitude stabilization? Right. So we'll use 3 magnetic torquers to stabilize the headlight. So before you execute a control maneuver, you need to stabilize, and we're going to use the 3 magnetic torques. We're going to have at least 3 magnetic torques. Okay. Design. We use the torques to stabilize the satellite.
Why do we need particle filters?
So what is going to happen is typically, if you these sensors, every sensor has a bias. You understand what a bias is? Can you tell me accurately how much is your height? What will that depend on?
The scale.
The scale, how accurately you can measure your height, right? The scale. How accurate can the scale get? Can the scale get perfect?
No, sir.
It just cannot get perfect, right? So whatever error you leave out, if you keep on measuring your height with that error is going to, no, let's say you measure your height, okay? There's always some error in that. Keep measuring and adding your height. What will happen to that error? It will compound, it will increase, right? That is the bias. Any instrument, any sensors you build, they'll have a certain bias in them. Now what you do is, if you combine, so these sensors will have bias, these sensors will have bias. You can use 2 set of sensors in a filter to account for that bias. One sensor will account for the bias of the other. You have to integrate them, you have to fuse them together to get rid of that bias. And you need something like a filter. So the filter is such that, so you realize, can you get angular rate readings from this?
No, sir.
The first, all right. So if I have a position, if can a GPS sensor give me velocity?
No, sir. No, sir.
Yes,
It can be calculated, right? So if you have GPS sensor, if I take 2 positions, right, and if I divide that by time, what that will give me the velocity, right? The velocity from that point to that point. If I have an accelerometer, if I use an accelerometer from that point to this point, and if I integrate it, what is it going to give me? Velocity. So you see, 2 sensors are giving me the same information, and I can look at these 2 sensors over a period of time and figure out which one is more consistent or which one has more error. That is where we use something like a particle filter or Kalman filter or an extended Kalman filter. You see the use? So that is the reason. And you have to do this because you cannot just go with sensor data. You have to have some kind of estimation involved. So you're estimating the attitude, relative attitude, and the rate of the spacecraft, the angular rate of the spacecraft. So you have to design that filter which will output that estimation. Okay. You have to do that with even with orbit determination as well. So that is what we were talking about, orbit determination. You fuse together the GPS data and an orbit propagation model. Instead of using an incremental sensor, there are no incremental sensors as such for propagating the orbit. You could use something like, you could do some reverse engineering to get the propagation data from attitude sensors, but accelerometers are not useful in giving you propagation data. So you have to use a GPS data which will give you absolute information and a orbit propagator to combine and give you the orbital position. There again you may have to use a filter. Okay. Now you have this, you have the three torquers. Can I erase that? So you have three magnet torquers to stabilize the satellite before executing. Can you just switch on the torquers and hope that the satellite will stabilize? What are you going to do? You're going to implement a control scheme. You understand this control scheme or a control algorithm? Control algorithm where you understand control, right? Automatic control, right? So here you need a control scheme or a control algorithm. And I'm going to give you an example. It's called a D dot controller. To use which will use okay. Try to make a connection. Do you think if you use magnet torquers, magnetometer, and gyros, can you visualize or can you imagine how we can stabilize using what is the control algorithm for stabilizing using these three systems or components? What will you do with the magnetometer? You'll figure out where the magnetic field is, right? Accordingly, you'll switch one or more torquers to align it with this. Why will you use gyros? To see if it is stabilizing, right? If the gyro value goes below a particular threshold, then you'll realize that your satellite has stabilized. Then you can stop your control algorithm, right? So this is, you use these three combinations to stabilize your satellite, and you have to develop a control law for that. And again, this can be taken up as a small project. The students will build their own torquers, buy a magnetometer, gyros, and then do some MATLAB simulations. So here this is a hardware in the loop problem. So this is a candidate for hardware in the loop simulation. How is it a hardware in the loop simulation? So typically you have is magnetometer, any magnetometer going to give you perfect measurements? No magnetometer is going to give you perfect measurements, right? So you need to include some noise characteristics or bias characteristics. Noise model, bias model, right? Where is that bias model coming from? You look at the magnetometer which is selected for the mission, go through the data sheet of that magnetometer, and extract these bias or noise models and put it in your simulations. Okay. So if you do those simulations, you'll be doing those simulations precisely for these sensors. For the sensors, specifically for the sensors and the actuators you have designed or you are going to use for the mission here. Okay. And similarly, yeah. Is this clear? How you're doing control? Here? Is it clear? You guys? It's okay?
Stabilization is not at all concerned with additive.
No, it's exactly. So you don't worry about where it is pointing. You're only worried about stabilizing. Then you go to the control. So here the goal is bring the angular rate, the desired angular rate is 0. That is what your goal is. So you're not really worried about where it is pointing. Okay. In 23, now you talk about control, right? So what we are going to, what I'm going to suggest is for the proposed mission, we go with one reaction or momentum wheel along the longitudinal axis of the satellite. So the satellite form factor is, let's say, what is the satellite form factor we decided? Or what is the possible this thing? Huh? 10, 10, 20 is the minimum we are going to go. So which is the longitudinal axis? The 20 thing is the longitudinal axis. So if you have, and again understand why we are doing that. So this would be a 10 by 10 by 20. Assume this, right? If my sensor is pointed like this, correct? Which face is facing sun? Possibly the longitudinal face, right? So even if it is, think about, even it is going like this, it's a polar orbit. Where is the sun in the polar orbit? That side, right? So if this is Earth, if I am Earth, so if the sun is, if the satellite is going like this, so let's say this is Earth, the satellite is going like this. Where is sun? It's on that side. So this face is facing sun, and then you're getting the maximum, the face which is capable of producing maximum solar energy is facing sun. Think about an equatorial orbit, right? Equatorial orbit, satellite is going to go do this, right? Even then, the longitudinal face is facing the sun. So that time again, you're producing maximum possible energy. And that is the reason if I put a wheel here, so when the wheel spins about the longitudinal axis, this is going to stabilize about what axis? About the longitudinal axis. So it's if we control it in this direction and keep spinning this the wheel around about that direction, it's going to keep pointed in this direction. Okay, so you don't want to stabilize it about this axis, right? You want to stabilize it about this axis. Okay, and then the satellite can do this. So you have your surface is always again perpendicular to the velocity vector. Okay. So with this, one reaction wheel, momentum wheel, and so what else do you need with this? Again, you'll need, what do you need? So are you going to just spin and the satellite will stabilize? You need another control law, another control algorithm for SIT satellite control algorithm for stabilizing, not stabilizing. Controlling SIT satellite such that the camera is facing Earth, solar cells are facing Sun, and the drag sensor is facing is perpendicular to the velocity vector. Such that one drag sensor is facing normal to the Now, keep in mind, some of you will realize that the velocity vector and the direction of motion are not the same. Okay. Why? This is just a reference. So where do you think is the velocity vector? Let's say at this point. Huh? It is not tangential. Okay. So there is a component, the velocity vector is generally like this. There is a radial component. Then there is a tangential component. This is the direction of motion, right? What is this velocity used for? That will help. If it was only this vector, it will potentially spiral it. Okay, because the gravity will pull it. So there is this vector counteract the gravitational force. Okay, so this is the velocity vector. So it's not necessarily perpendicular to that. It's perpendicular to the what we call RAN direction. Okay. Now you'll come across this if you do your simulations. When you go deeper into the mission, you'll realize this when you start doing your simulations. But for now, let's just take it that it's the velocity vector. Okay. Two. Camera is facing Earth, and the solar cells on longitudinal phase are So the control algorithm is such that you have this thing. So you could now you don't necessarily have to use the wheels alone. Okay. When you design a control law, you could potentially use the wheel, the one wheel, and also your 2 or 3 torquers. You can use a combination of the magnetic field and this wheel to do control. For stabilization, you'll strictly go with magnet torquers. These are not good for stabilization. What happens is if you stabilize with wheels, it may get much more unstable. Okay? Because see, wheels, what happens is magnetic field. Magnetic field is instant, right? Once you switch on, the field will almost immediately the field will attain its maximum strength. Does that happen with wheel? Wheel will slowly start spinning. When the wheel starts spinning, the satellite will start rotating, start tumbling. Okay. So if it is already tumbling and you start rotating the wheel, it will tumble even more. Okay. So that is the reason we try to use the magnet torquers, and this is a much slower control process. It will stabilize over several orbits. This will happen instantaneously. That control action is pretty fast. The switching on of the actuators is fast here, but the control action takes some time. It may take several orbits before the satellite is stabilized. However, here the actuators take time to reach their maximum speed, but the control action is immediate. So think about, have you tried to stabilize your car when it is out of control? Nobody has driven a car out of control. But have you seen videos, or have you seen where they're trying to stabilize the car when it is unstable? If you try to do that with wheel, what happens? It may become more unstable, right? So that is this thing. So what happens if you do a jerk with your steering wheel? Have you tried doing that on the road? It will tilt off, right? So that the camera action, the reaction wheel control action is pretty immediate, pretty fast. Magnetometer or magnetic torquers will slowly do it, will gradually do it and stabilize. Okay. All right. So this is now you're seeing how big this becomes. Okay. This since for the payload we have thought, for the payload we have imagined, attitude control is a pretty significant subsystem. Now you have asked for a good complex payload, so you will get a complex attitude determination. Not too complex, but it is still pretty complex. Okay, and we have to work out the details of this. And the limitation with this is a lot of this is not taught as part of courses. For example, there is very little which gets taught as part of the mechanical engineering curriculum. Some of this gets taught, but not a whole lot. The control algorithm, you do teach automatic controls, but again, before you do control, what do you need? So control law is again a lot of mathematics, right? Before you want to control, what do you need to know? What are you trying to control? You're trying to control the state of a particular system, right? How do you get to the state? What allows you to output a state? You know what a state space model is? What is a differential equation? What is a differential equation in mathematics? What does differential equation give you? What is mathematical modeling? Okay, what is mathematical modeling? Tell me.
Correlate position, velocity, and then acceleration components with respect to differential.
Okay, that is one answer. What is a mathematical model?
Set of mathematical equations which represents a physical problem.
Physical system, okay. But what does it relate? It relates essentially two things. It's the relationship between input and output of a system. Okay. Input-output relationship is nothing but a mathematical model. Right? You need to develop before you do control, before you learn control, and this is where the limitation is. Electrical department or electronics department, you will do a lot of control, right? Control is a big thing, but the dynamics, you don't do a whole lot of dynamics, and that's where the mechanical department folks can help you do the dynamics. Dynamic modeling is nothing but writing a mathematical model or expressing the input-output relationship. How do you control the output? By giving a certain input, right? Can you control the output directly? You cannot do that, right? So the input-output relationship here, what are you trying to control? The output. So what is the output here? What is the physical quantity? What are you trying to control? In this, what are you trying to control? So this control algorithm, what are you trying to control? What is the physical quantity? Angular rate, right? Can I say I am controlling the omega, small omega of the spacecraft, right? That is the output. Got it? What is the input? Current
through the target.
torque. So your current will relate to torque, but essentially you're trying to control or input a particular torque so that the angular velocity is controlled. You see that? Now you have to know how to develop that relationship between the torque input and the angular velocity, right? So if you want to control the position, right? What are you inputting? Is position an input? Position cannot be an input, right? Position has to be output. So what are you inputting? Force. So if you apply a force, what do you get? Huh? Change in momentum. That is Newton's law. If you apply a force, it will affect in change in momentum, and then if that change in momentum will ultimately give you position. So that will change the position, and that's how you try to control. So you have to understand that mathematical model is an input-output relationship of a system, of any system. Okay, and you need to learn that is a big part of all this that we discussed. You need to develop that and apply control law. So where are you applying the control law? Does it coming is this control? So the control law is, if you do the block diagram, you understand this block diagram? You understand this block diagram? The input output, what are you trying to control? The plant or process. So you need to understand, if you apply a certain input, what is the output? Okay. How do you affect that input? Using actuators. You need actuators, right? How do you manipulate actuators? Using a control system. Okay. And what are these? What do you use for this feedback? What do you use there? Sensors. You'll use sensors to measure the output, send it to the control system. Okay, the control system will decide. Control system is, what is a control system?
It can act based on our
Is it a system or control system?
So this itself, the entire thing would be a system, right? The control, this is the control part where you can call this entire thing a control system. That is also possible. Here, it's more like a control algorithm. Okay, this is the program or the control law which decides, which makes the decision. Control law is simply the mathematics or the logic of it. Okay, this would be a control system would simply be another computer, a small processor, which will be able to manipulate the actuators so that the plant will give the desired output. So every time the output is measured, and what is minimized? The error which is ultimately what you want is this error, the input, and this relation should be the difference between the input and the output is 0. When the input output is 0, what is going to happen? There is no input, right? There's nothing going in, and that is when it has reached that equilibrium state. Okay, and you need to do this for all of this. You need to model the develop a dynamic model of the satellite. Okay, the angular rate torque relationship model, and then develop your actuators. Actuators here are two types of actuators, right? We are looking at two types of actuators. What are the two types of actuators? What are the two actuators we are using here?
motors.
Correct. So motors is part of it, but what are the two actuators we have identified here? Torquers, magnetic torquers are actuators, right? Will it actuate the satellite? You understand actuators?
Yes.
In your body, what are actuators? Muscles are your actuators, right? So these muscles actuate your hand. You see that? So here the actuator, one set of actuator is the torquers. So when you activate the torquers, they are going to try and align with Earth's magnetic field. So they are actuating the satellite. You see that? They are acting like muscles. What is the other actuator? The wheel. Okay, when the wheel spins, it's going to make the satellite spin. So that is the other actuator. You see, there are only angular actuators here. Are there translational actuators? What would be a translational actuator? Thrusters. So we are not going to use thrusters just because we don't want to create any problem for the triangle. Okay. We don't use translational actuators in space a whole lot. We use a lot of angular actuators. Okay. Rotational actuators, so to say. Now let's finish this. What else is the derived mission requirement? There's one more last derived mission requirement. I want to finish up with that. What is that? What is the last derived mission? What do you need? So you have identified pretty much every subsystem. Now what do you need? the structure to case this or to house. Okay. You need a chassis. One, you need a chassis. Okay. In a vehicle, let's say in a car, you know what a chassis is, right? So what is the chassis? Can you see the chassis of a vehicle? Yeah. So chassis is something where it supports the entire structure of the car. What is a chassis in your body? The skeleton is a chassis. Now what do you need over that skeleton? Surface to cover it, right? So for a satellite too, the chassis will only be the skeleton. Okay, you can mount all of this on the chassis, but you need something to cover it. And those will use multifunctional PCB panels. PCB panels, you understand PCB panels? So I'm going to show you satellite. You can design, typically you can do metal panels as well, aluminum panels, but it will make the satellite a little too heavy. So what we are going to do is, we are going to use PCB panels to one, cover the satellite, plus it will also be used for mounting the solar cells. Okay. So that's the reason I'm saying not just the solar cells, but also other cameras, sun sensors, temperature sensors, all that. So that is the reason I'm calling them multifunctional PCB solar panels. They are used as structured solar panels, temperature sensor, sun sensor, camera, and these can be designed, and these can be very useful, right? So what you're going to notice is, if you want to avoid a lot of wiring in a satellite, you can use the traces inside PCB. You make connectors inside PCB and then use them to wire your satellite. So this can be a really innovative project. Just the design of PCB panels. You can design PCBs, simple PCBs, and you can print PCBs as well here, right? How many layers can we print here? At least 2 layers. You don't have facility. So we can procure a PCB printing machine, very simple, like 2 to 4 layers should be sufficient for this. Yes.
Even instrumentation is single layer.
Single layer PCB. Okay. But when we go for the flight PCB, we'll get it fabricated from outside. But for EDU, we'll at least get a simple PCB printing machine, which may not be that expensive, to do our PCB design ourselves. So what we can do is a PCB printing machine, and plus for this, the structural chassis. If we get a 3D printer, we can go back and forth with prototyping design, and have a nice structure developed for the engineering design unit and the flight model. If we have that, then you can physically feel that. Okay, you can assemble all these things. present a prototype to potential funding agency or to potential stakeholder. Okay. So if I would suggest I look at that. But anything else we are missing as part of derived mission requirements? So here, what I'm going to point out is we have looked at mostly functional requirements. You see that? We have not really looked at the performance requirements. So we have to look at performance requirements, and we'll do that when we do the detailed design. We can come up with performance requirements. For example, things like what is the pointing accuracy you need? What do you think is the pointing accuracy we need? Do we need arc minute, arc second accuracy? You understand what pointing accuracy is? How accurately do we need to point to Earth? If you are off by a degree, will it be okay?
Yes.
If you are off by 5 degrees, will it be okay? If you're off by degree, will be okay. If you're off by a couple of degrees, also will be okay. 2-3 degrees. 5 degrees may be too much, but I think even that might be okay. If we design a nice system which will measure the drag in all directions, even 5 degrees off, being off by 5 degrees will be okay. But nothing beyond 5 degrees. Okay, that is one of the performance requirements. So if you're off by 5 degrees for a camera, will it be okay? So you see, this is Earth, okay? How big is Earth? If you're in space, you have a camera, you're off by 5 degrees. Will you be able to still see Earth? You'll be able to see Earth. Why not? Part of it. You have to be really off to miss Earth. Even in the low Earth orbit, Earth is huge. So you're not going to miss a whole lot if you're off by 5 degrees. Camera wise, don't worry about the. I think the concern is that we may not get a good picture. But I understand. It's not like it's not like a selfie. If you're taking a selfie, if you're off by 5 degrees, will it matter? Huh? Yes, right. So the distance is pretty huge. If you're off by a little bit, you'll probably be okay. If you're taking selfie and you're off by 5 degrees, it matters. You may get only one eye. But it may not happen so for a satellite taking picture of Earth. You may not get SIT or Tumkur, but you'll get a nice view of Earth. Okay. So we have to look at performance, but what we'll do is we'll look at that as part of the detailed design. Any questions? So you want to come back after a break?